Today we shall start again recapitulating what we did in the last lecture, the new things those we learnt, and then we will do something more with kinetic theory, and plan is that towards the end of today's lecture hour, I will tell you briefly about non-ideal situations. Why non-ideal situations are important? It is important because of the fact that you know ideal gas, what we are dealing so far, there is no interaction, and if there is no interaction, there is no phase transition possible. Most of the situations, only one exception to be correct, I tell you that without interaction phase transition happens, that is called Bose-Einstein condensation. I quoted this name because it involves the name of a great Indian scientist Satyendranath Bose, but that is essentially a quantum phenomena happening at very low temperature, where there is no interaction in that sense. It is the nature of Bose particles, or rather to be precise, the statistics of Bose particles that give us the phase transition, so called formation of Bose condensate, which at least you know about them in popular level at least. But what I want to tell you at the moment, that we are dealing with ideal gases, and these ideal gases cannot lead to any phase transition because there is no interaction. So, first and foremost criteria of a phase transition should be interactions between the particles I am dealing with. So, that is why I will bring in some non-ideal nature and tell you what is vapor and how does the PV diagram for a liquid gas transition looks like. But before that, let us start with what I wrote here, recapitulating what we learned new thing. I talked about pressure. Okay. Pressure is related to m n L cube V RMS square. I remind you what is V RMS square. V RMS square, actually it is a vector dot product. If you like, I can decompose it in 3 components. Z square and divided by 1 over n. So, that it is the average. Okay. It is the average, and I am summing over all the particles I have. Okay. So, this is the average information that is carried here, and this is mass of each gas molecule, n is the number of particles in the container, and L cube is the volume of the container, where I chose a cube, but it is not essential to choose a cube. You can have a sphere if you like, and this you can write further as P is equal to 1/3 rho V RMS square, or I can go further, P V is equal to 1/3 m V RMS square, which I can write also as, if my mass of each molecule is m, m n V RMS square. So, this is, I will drop this expression RMS in the subscript from the time being, and I will be assuming that I am dealing with average velocities, which are root mean square velocities. Now, question was, how do you relate it to temperature? So, I have pressure, volume, but they are related to microscopic objects, which we can never measure in experiments. What we measure with a thermometer is temperature. So, it is important that this relation should be connected to temperature. So, what I did first, ideal gas equation of state, what is an equation of state? Equation of state is something that connects the different thermodynamic variables, or I am talking about chemical system involving P, V and T. So, my equation of state will be something that connects pressure, volume and temperature. This is true for an ideal gas, and this is a combination of Charles's law, which says either P is proportional to T if I keep volume constant, or V is proportional to T if I keep pressure constant, or it's Boyle's law, which tells me that PV itself is a constant if I keep temperature a constant. Okay. These can be verified for a gas which is at very high temperature and very low density, which is the limiting situation for any real gas, where I can approximately treat it as an ideal gas. Okay. So, now I put these things together, this equation I got here, this is my ideal gas equation of state, PV is equal to nRT. I can simply write PV is equal to N kBT, and then what we have found out, very important expression, that half V RMS square is equal to 3 by 2 K BT, and then this gives me very important relation that temperature is defined in terms of average kinetic energy of the gas molecules. This I can physically interpret in the following way. If I increase the temperature, I expect the gas molecules to have more kinetic energy. So, if you can think of this way, kBT has dimension of energy, this I will call the thermal energy. If you have higher and higher temperature, they will have more kinetic energy, the gases will move with more kinetic energy. This is something I physically expect, and this is what kinetic theory tells me about. So, once I have this, I have a new definition of temperature. So far we were dealing with definition of temperature which we measure in thermometer, that is in our calorimetry, but kinetic theory gives me a more fundamental definition of temperature, that mean translational kinetic energy is related to 3 by 2 kBT. Okay. Now, these two taken together, PV is equal to this, and kinetic energy for n molecules, if I have n molecules, total kinetic energy will be V RMS square 3 by 2 N kBT. If I have both of them together, then I arrive at a expression PV is equal to 2/3 E translational, and it is all kinetic. I told you why it is kinetic. It is kinetic because I am assuming ideal gas, and ideal gas does not have any potential energy because there is no interaction between the molecules. This is the first point, and second point I said that it is all translational because I am dealing with a monoatomic gas and there is only translational degrees of freedom. Okay. So, if I increase the temperature, translational degrees of freedom, translational energy increases, and that defines my temperature. This is an equation in which I have completely gotten rid of temperature. I am connecting pressure, volume to the average kinetic energy of the system. Okay. And secondly, I mentioned briefly that this is a very sacrosanct equation because PV is equal to NKT is valid for ideal gases which are classical, which are very high temperature, low density situation. I cannot write a similar equation if I go to very low temperature, but as long as I am dealing with a monoatomic gas and as long as I am treating ideal systems, that means there is no interaction, I arrive at this equation. Even the Bose gas I was mentioning before, you can have an equation like this. And I told you that these 2 and 3, these two comes from the fact EP energy of a particle, simply I am doing Newtonian mechanics. So, any particle with momentum p with energy p square by 2m. So, there is a 2 factor coming here and 3 coming in because of the factor that I have considered 3 components of velocity. Usually our world is, in our conventional physics, classical physics, world is 3 dimensional, as 3 components of velocities, and there is no difference between these 3 components of velocities. There is something called isotropy, which I referred to it many times. Now, I told you something very important. Since these 3 are completely equivalent, then I can have a equipartition of energy. Okay? I can have an equipartition of energy. Okay? What do I mean by equipartition of energy? Equipartition what do we mean by equipartition of energy? That my V square, I can think of it's consisting of 3 pieces, Vy square and Vz square. This is my V square. Okay? So, kinetic energy has contribution from x component of velocity, y component of velocity and z component of velocity. So, since Vx, Vy, Vz are equivalent in the probabilistic sense, these are all RMS I am talking about, I can write it as 3 Vx square in the average sense. Okay? Since I can write it as 3 Vx square, I get 3 Vx square if I multiply by 1/2 m is equal to 3 by 2 kT, kBT. So, K always stands for the Boltzmann constant, even if sometimes I may forget to put this B subscript here, though immediately give me half mVx square is equal to half kBT. So, you see the kinetic energy, if you like, contribution to the kinetic energy for the x component of velocity half mVx square is equal to half kT. Similarly, there is nothing great about x, I can write half mv y square as half kT. This is equipartition, which I said that 3 components of velocity, 3 components of velocities okay, and energy is apparently half kT for each molecule on an average in each direction. Okay. Well, what I mean by each direction is clear, that half mVx square is equal to half kBT, half mVy square is equal to half kBT, and these 3 adds and gives me 3 by 2 kBT. If I have for n molecules, then half Vx square okay, will be first half n Vx square translational kinetic energy associated with Vx, this will be this quantity which will be n by 2 kT. Okay. So, this is called the equipartition energy. Whenever you have this type of form ideal gas, then you can ask me that what is the energy associated with each degrees of freedom. I should be very careful when I mean what do I mean by degrees of freedom. Okay. Let us recall a bit of classical mechanics. Okay. In classical mechanics, if a particle is moving along a line, let us say x axis, then I can immediately characterize the particle by x and also velocity Vx. Okay. If it is under a force, then I can say x and Vx. So, x if you like is the degrees of freedom. Okay. You can also think of Vx is one of the degrees of freedom. If you have an x, if you have a Vx, so there is 1 degree of freedom. Okay. Now, if particle is allowed to move on the floor of this room, you have a Vx, similarly you have a Vy, right. So, I will say x, y, that gives me the coordinates, it has 2 degrees of freedom. Similarly, if I have a particle moving anywhere in this room, I will need 3 coordinates x, y and z, and correspondingly 3 components of velocities Vx, Vy and Vz. So, essentially I have 3 degrees of freedom, and I am saying for each particle on an average, okay, on an average, if temperature is T, I am talking about equilibrium situation, if temperature is T, for each particle on an average, for each degree of freedom, that means associated with each Vx here, x has no role to play because it is free particles, ideal gas. For each Vx, I will have an energy, average energy, which is half kT. This is called equipartition of energy, and this is very, very important. Now, if you think of n such particles, where this is your capital N, you know you will need many 3 for each, 3 for each particles. This I explained for one particle. Now, you may have n particles. So, n particles each moving in 3 dimensions. So, I will have Vix, Viy, Viz, okay, Viy, Vix, Viy and Viz, and now for each of this average kinetic energy I will have half kT, okay, n number of particles because they are not interacting, and I will have same term for Vy n kT, and I will have a similar term half n kBT for this, and the total will be 3/2 n kBT. Okay. This is how I get to this expression using the equipartition, or rather kinetic theory tells me about the equipartition theorem. Now, I can go further. I told you there could be other special cases. For example, I can get harmonic oscillators which have energy p square over 2m, and this is the potential energy. Okay. This is the form of potential energy for a harmonic oscillator, and if I have this potential energy, then energy of this average energy of this harmonic oscillator, when this oscillator is at a temperature T is kT, kBT. This is equipartition applicable to harmonic oscillators. Okay. Whenever you have this quadratic form, okay, here ideal gas I was only having translational degrees of freedom, but here you see I have x and p both I can treat as independent degrees of freedom, both are contributing to my energy and both is quadratic in form. This is very, very important. So for ideal gas I was calling my degrees of freedom only as Vx, Vy, Vz, okay. But when it comes to harmonic oscillator, where force is of the form minus kx and potential is of the form half kx square, as we have learnt in my mechanics course, then total energy is this form, and I have effectively 2 degrees of freedom which are p and x, and both giving me half kT. giving me average energy of an harmonic oscillator is kBT. Ideal gas molecules, it is half kBT, and harmonic oscillator, it is kBT. I just argued it out using the equipartition, which I try to invoke upon you using the kinetic theory of gas. Now, this is the average for harmonic oscillator. If you have n non-interacting, this word is very important, non-interacting harmonic oscillators, then simply you can write this. Now, you see these harmonic oscillators are not oscillating in one dimension, rather in 3 dimensions, then you will have a term 3 sitting here. Okay? That tells us a lot about equipartition of thing. I explained to you what each degrees of freedom means, and then I will proceed further to calculate something measurable in the experiment, which I briefly touched upon in my last lecture, that I talked about specific heat, and specific heat can be of 2 types. Firstly, you calculate specific heat keeping volume of the container fixed, that I call CV. Okay. This is CV, okay. And then I can have it keeping the pressure constant, measure the specific heat, which I can write in general C is equal to dE dt. Okay. You know heat energy, specific heat you define in calorimetry in terms of amount of heat that is being absorbed or released in raising the temperature. Here we know heat is an energy and we are dealing with energy here. Specific heat is equivalently related to change in this derivative, simply tells me this is the change in energy, average energy, if I change temperature, or if I use more familiar notation for you, it is del E del T. Okay. You change temperature by an amount delta T, and that this is the change in energy. You take the limit delta T tending to 0, you can write in your calculus form. If you keep volume fixed, then it is called CV. If you keep pressure fixed, it is called Cp, and for an ideal gas, I just quote it without any proof or further. For ideal gas, Cp minus Cv is R. This I will try to elaborate more, and there is a ratio gamma which we will calculate Cp by Cv, which I will use when I go into thermodynamics. I talk about adiabatic processes, then these things will be useful. Now, if you do this, you can immediately see Cv, let us focus on only Cv. For an ideal gas, it should be 3 by 2 Nk B, which is called the Dulong-Petit law. If you do it for an harmonic oscillator using the equipartition, you do it for an harmonic oscillator, this expression 3 Nkt, which I have wrote here, gives me Cv is equal to 3 kBT, 3 Nk. Okay. So, you see these are called Dulong-Petit's law. Ideal gas, it is 3 by 2. I told you in the last class this 3 comes from dimensionality of the thing, and here it is 3, because where do you get the other half factor form in the harmonic oscillator? Because in this harmonic oscillator, if there is a half k x square, which is very important, because now you have 2 degrees of freedom in that sense, one given by x and one given by p, both contributing half kT to my average energy. So, harmonic oscillator, this is Cp, this is Cv, and you can calculate Cv, Cp using this relationship you have here. You remember R is equal to Nkv. But coming back to the ideal gas, So, when I talk about CPCV, it is ideal gas, harmonic oscillator, it is just 3 NKB. Now, coming back to ideal gas, so far we have been talking about monoatomic, and hence I was talking about only translational degrees of freedom. And now, if I have a diatomic gas, okay, so go beyond monoatomic, you do diatomic gas. Okay. All you have to do, remember how many degrees of freedom do you have, and how does this degrees of freedom contribute to your energy? Degrees of freedom contribute, all degrees of freedom contribute half kT to energy. Okay. So, diatomic case, diatomic. So, first thing is translational. Again, this molecule is moving in a 3-dimensional container. So, I know again there is no interaction. So, it is ideal gas, three-dim container, and I do not consider any interaction. So, one is translational degrees of freedom. How many? 3. So, what do they contribute? 3 by 2 kBT. Okay. But that is not the end of the story. Okay. Let us take an oxygen O2. Okay. So, you have 2 atoms. Okay. There are translational degrees of freedom. But of course, if I take a dumbbell like shape, I know molecules can rotate. If I take an axis, it can rotate about this axis. I know what is rotational kinetic energy. I have done it in my rotation chapter in mechanics. So, I have a rotational kinetic energy. And what is this? These are 2 axes of rotation. If I rotate about 2 possible rotations, and this gives me half I omega 1 square and half I omega 2 square. So, I have fixed this axis and I am allowing rotations. I can have 2 rotations. So, those both of them giving me half I omega square. So, I have 2 degrees of freedom here, and remember this is also what I said, quadratic in nature. If that be the case, I immediately know that I am going to get a 3 by 2 kT here, I am going to get half kT for each rotational degrees of freedom. So, total I will be having total average energy for a diatomic molecule is F by 2 kBT, and then specific heat, if I take n such molecules, average energy will be 5 by 2 n kBT, giving me a specific heat, that is 5 by 2 nk. So, you see that number of degrees of freedom I increase, I get a different expression for my total average energy. This is the total average energy for n such diatomic molecules, and once I put that in, the expression of specific heat which I experimentally can measure, okay, that goes into 5 by 2 instead of 3 by 2. Next question you will ask, what will happen as a polyatomic molecules. So, for a polyatomic molecule, you have to be bit more careful, and one has to go further than this diatomic. Now, let us go to polyatomic. Now, I have many atoms forming a molecule, polyatomic situations, and I will use this equipartition theorem which I talked about. Roughly, if you have a polyatomic molecules, you can think of it as a rigid body. For example, firstly, crudest possible approximation, let us consider it as a rigid body. Okay. Now, if it is a rigid body, you know rigid body, mechanics teaches us a rigid body has 6 degrees of freedom, okay, 6 degrees of freedom. Why 6? You may be knowing only a rigid body rotating about a fixed axis, and you know L is equal to I omega, but truly speaking a rigid body can rotate about a fixed point. What do I mean by that? It is rotating about a fixed point means instantaneous axis of rotation passes through these points. Okay? Or since that can happen, at the same time I can always give a translation to any particular point. You know the concept of center of mass. So, let us focus on center of mass. I can say rigid body is rotating about its center of mass, and then the center of mass may have a translational degrees of freedom and it can move in any direction. So, there will be 3 translation and 3 rotations. Okay. Since you may not be very familiar with this 6 degrees of freedom business, let us invoke upon you that how does this 6 come. Okay. What is the definition of a rigid body? Definition of rigid body tells you that distance between the any 2 points in the rigid body is fixed. Okay. Any 2 points is fixed. So, if I put one particular point, a mass here, then it has 3 degrees of freedom, because it has no constraint with it. This is my first particle, this is my second particle, this is my third particle. Okay. Now, first particle has 3 degrees of freedom, 3. What about the second particle? Second particle can do whatever it likes, but it has to be at a fixed distance from the first particle. So, second particle has degrees of freedom 2, okay, because it has to maintain a distance, as I said in the diatomic molecule case, okay, to 2. And now, third particle has to keep a fixed distance from 2 and 1 both. So, it can move only in 3 dimensions actually, but always keeping this constraint that it has to be at a fixed distance from 2 and from 1. So, it has 1. Okay. This gives me 6 total degrees of freedom of this system of particles, but if I, what about if I bring a fourth particle here, the fourth particle, okay. Well, fourth particle has to keep a fixed distance with all the other particles in the business. It has to keep a fixed distance from 1, 2 and 3. So, it does not have any free degrees of freedom in that sense. So, total degrees of freedom is 6. I told you that 10 to the power 23 particles if you have to deal with, you cannot write 10 to the power 23 second order differential equations with given the force form, and you cannot solve it for that matter. Okay. So, but what helps us in mechanics is this rigid body approximation. So, this is a rigid body approximation which you may not be very familiar with, that is why I am spending some time in this rigid body thing. Rigid body approximation. Why it is approximation? There is no ideal rigid body in world. You already know, I am pretty sure of, that Einstein's theory of relativity tells us that no information can propagate at a speed which is greater than speed of light. So, I cannot have anything instantaneous in our real world. Okay? There is always a time required, but rigid body assumes that if I give a disturbance to any point of a rigid body, okay, any point of the rigid body, then rigid body should, information should propagate to other part of the rigid body instantaneously, which is not possible, and that is why rigid body is an approximation, but that is a very good approximation. And secondly, I have 10 to the power 23 particles, let us say in a rigid body, but I deal with just 6 degrees of freedom, 3 translational and 3 rotational, and you know that simplifies life to a great extent. Okay. If that be the case, what is the polyatomic molecule energy? There are 6 degrees of freedom, each giving me half kT, and n of such molecules, I will simply have 3n kT. So, number of degrees of freedom is actually doubled. Okay. So, specific K2 will be 3n K, but that is not the end of the story. I am assuming, I said it is a rigid body approximation, there could be some vibrational mode. And if you count these vibrational modes, there could be f such vibrational modes. So, you will be having for each vibrational mode, you will have 3 kT, that is coming from my rigid body thing, and then I will have f by 2 kT for possible vibrational mode of the rigid bodies, and this will be my total energy, and accordingly the specific heat gets modified. So, this is all I wanted to discuss about specific heat, equipartition, and if you follow your book, you will see there are many discussion on this, and also you can refer to Professor A.C. Verma's book, where also things are done at some length. So, what I have done so far, that P is equal to, again I write m n v square, this is V RMS square, and kinetic energy gives me the proportionality to temperature. V square is proportional to kBT, if you like. Okay. This is a very fundamental thing of kinetic theory of gas, what I am dealing with. Now, if I have a different approach, which actually I pick up from Professor Harish Verma's book, you can see if you have one gas for which PV is equal to m n v square. Now, you can motivate yourself that actually temperature will be a function of half mv square. Okay. This functional form I derived using the ideal gas equation. Okay. I use the ideal gas equation to arrive at this functional form. Physically, I argued that temperature is increasing, mean kinetic energy of the molecules I am considering, they must also increase, and this is the what this functional form tells us. So, it should be a proportional from my physical arguments, but this can be elaborated in the following way also. If I take the same gas in the same container at a different temperature and pressure, which I know, for example, this temperature which I measure could be, if you like, some temperature which is of the order of 273.16 absolutes, and you can write m n v naught square. Okay. Then you immediately know P by P 0 will be equal to V square. I remind you, these are all RMS velocities. So, V square by V naught square. Once you have this form, now you recall your Charles law. P is proportional to T for a given volume. You can write V square is equal to P by P naught into V naught square. And if you remember your Charles law, and if you know that P naught and V naught are constant for a gas, okay, you immediately arrive at something which is V square is equal to V naught square by T naught into T. So, that gives you precisely the proportionality I am talking about, and then kinetic energy, if you V square, if you extract the kinetic energy from this, this is a constant for a gas, given gas, this is a constant. So, you get V square is proportional to T, and now how do we set this proportionality? Just by argument, hand waving argument. If I make it energy, and dimensionally this quantity should be Boltzmann constant, and I can have some number, this number I argued to be 3 by 2, okay, because dimensional analysis argument cannot give me whatever this number A is. Okay. having done all these things so far, I will proceed and tell you little bit about how to use kinetic theory for different situation, and that will probably end today's whatever I wanted to do. So, if I mix two gases, but everything is in equilibrium, I call it thermal equilibrium, which already tells me there are other equilibriums, and it will be discussed in the thermodynamics part of this lecture series. Thermal equilibrium means temperature everywhere in the gas is the same. So, I do not need to bother about the temperature which is same everywhere, and if it is this, I have two gas molecules, one is having mass m1, other is mass m2, I must have m1 v1 again in average sense, that is RMS, m2 v2 square. Okay. So, this is an important thing. If those two gas molecules are in equilibrium, I must have these condition satisfied on an average. Okay. From this, you can calculate the RMS velocity. If I give you the temperature and RMS velocity of one of the gas molecules, you know what you can mathematically calculate what is the RMS velocity of the other one. Okay. So, now second we will proceed further. Okay. Now, let us proceed. Do I have Boyle's law? P V is equal to constant in a given temperature. What did I find out for P V? Okay. P V is related to, as I wrote, 1/3 capital M, 1/3 capital M small n V square average. Okay. Now, this is my PV. Now, I have already told you this fellow is nothing but proportional to temperature. Okay. We have already used Boyle's law in getting into this equation P is equal to 1/3 m n V square, but I will make things slightly more complicated. Rather, I am doing a self consistency check here. Just I am saying that if this quantity is temperature, proportional to temperature, so this right hand side must be equal to a constant if temperature is constant. So, PV is constant if T is constant, because right hand side of this equation is entirely proportional to temperature, and this gives me my Boyle's law. Similarly, you can argue about Charles' law. If you keep phi fixed, okay, and this quantity is proportional to temperature, so if you keep V fixed, okay, so P is proportional to temperature, that is your Charles's law. Okay. Now, let me see what else we can talk about. Okay. Okay. Now, Avogadros law. What does Avogadro say? That given T, that means I fixing the temperature, and P equal volumes of all gases have equal number of particles. That is what we say the Avogadro number. If we call 1 mole of the sample, so equal volume, given temperature, given pressure, I am fixing temperature, I am fixing pressure. Okay. Now, what is PV equation for the first? 1/3 N1 M1 V1 square. Okay. Well, sometimes I will put this bar to remind you that these velocities we are talking about are the average velocities. Now, for the second gas, I do have PV is equal to 1/3 N2, okay, M2 V2 square. This is my PV equation, okay. Volume is same, but there is one more to this which I wrote earlier. This only tells us nothing, because I have quantities involving N1, M2, V1, V2 to arrive at this claim which Avogadro made, okay, Avogadros hypothesis, that if I want to do that, I need one more. Since temperature is fixed, T is fixed, I must have this quantity which I wrote few minutes back, that when you have two gases at same temperature, this must be satisfied. Once you have both these together, put both these equations together, which gives me N1 is equal to N2. So, completely see, Charles and Boyle's law were somehow expected to come out of it, because in arriving at this equation, at some point PV equation, some point I used ideal gas, okay, to at least get the energy. P is equal to 1/3 MnC square, PV is equal to 1/3 MnC square or MnV square, whatever I derived from the kinetic consideration. But to connect it to energy, PV is equal to 2/3 E. What I needed is ideal gas equation, or some way I inspired that using the definition of absolute scale and the thing I did from Professor A.C. Verma's book. But what is not expected here, okay, that it also gives me the Avogadro hypothesis. Whatever other laws of thermodynamics, laws of thermal physics I know, can be arrived at similar fashion. Okay. So, you see that microscopic physics, what I am doing here, okay, are all will follow or lead to the macroscopic equations I know from my early school days. For example, second examples will be, for example, Dalton's law of partial pressure, Dalton's law of partial pressure, which says that you have many types of gases, let us assume all of them monoatomic, and then I put them in a container. Okay. So, I put them in a container, I am asked what is the pressure in the container. Okay. It is called partial pressure law, which tells you that if I have, for example, some types of gas molecules, then this total pressure which is being exerted on the wall of the container have many pieces, P1, P2, P1 corresponds to fast gas. Physically what it means, that if I only had, okay, the gas number 1 in the same container, the pressure exerted by the gas number 1 to the container, okay, would have been, okay, P1. Similarly, if there were no 1, 2, 1, 3, etc., only second type of gas, then the pressure exerted will be P2. But when all of them are put together, then it is P1 plus P2 plus P3 and so on. Well, this is partial pressure. You should bear clearly in mind what I mean when I say P1 or when I say P2. If I remember, how do we define pressure? Pressure we defined in terms of momentum transferred, right? Momentum transferred per unit time. So, momentum transferred per unit time divided by L square, this area of the container. So, it was important that momentum transferred, okay. Now, first molecules, they are all independent, non-interacting, goes and hits this wall, okay. That will lead to a momentum transfer delta F1, and if I take all of these first molecules, then the momentum transfer will be simply F1, okay. Now, second one will again give me a momentum transfer of F2. So, net momentum transfer will be summation over I Fi. This is the net momentum transfer because of the all molecules present in the container per unit time, and net momentum transfer will be this quantity I have written with summation here, where sum extends over all the molecules I have, and then if I calculate pressure, which is just dividing the net momentum transfer per unit time, which I was interested in. So, pressure that this system of gas molecules will exert on the wall of the container will be given by net momentum transfer by L square, and which you can see P1, P2, etc. So, P1 is just due to momentum transferred by the gas molecules 1, P2 is just the momentum transfer by the gas molecule 2, and so on. Third thing, or the last thing in this regard, so that tells us the physical origin of the Dalton's law of partial pressure. Finally, if two gases maintaining same pressure and temperature, we allow it to diffuse, you can very easily argue that diffusion rate, what should be the diffusion rate? How fast they diffuse? It diffuses because they have a RMS velocity and they want to spread out. So, one molecule spreads into the other. Now, rate, if I say, can simply be proportional, rate simply be proportional to R1 by R2, simply be proportional to V1, again RMS, remember whatever I am talking about RMS, and we already have seen RMS, Vrms is simply given by 3p by rho. So, if you substitute this, the rate of diffusion will be inversely proportional to density. So, how do you get it? I repeat the argument. The argument is the following, that two gases same pressure and temperature are allowed to diffuse, one is diffusing into the other, gas is coming out of a cooking gas cylinder and diffusing into air. So, I expect the rate of diffusion, how fast it diffuses. Okay. Now, R1 by R2 should be proportional to how fast the gas molecules are moving. So, that will be given in terms of these RMS speeds, and if this is given in terms of RMS, we know the expression of RMS. Okay. If I substitute it back here, I will find out this rate is proportional to, okay, inversely proportional to the square root of density. Okay. This is called the Graham's law of diffusion. All these things we have said are experimentally measured, okay, and kinetic theory, though in kinetic theory we are talking about a microscopic description given in terms of velocity distribution, which I told you that there is a speed distribution, there is a velocity distribution, there is an RMS speed, but all the experimental observations which we make can be reflected here. Since I talked about last 2 minutes of today's thing, since I have talked about so much about the diffusion in last 2-3 minutes, I will try to tell you something. Now, we have assumed all through, which I will complete in the next lecture, that I have been telling you that see, I am dealing with gases which are not colliding except for the wall. When I calculated, if you remember, the momentum transferred and hence the pressure, I was specific, this particle is not having any collisions, it is successively bouncing back and forth between the two walls of the container. And this is obviously a very drastic assumption. Okay. Now, there is a concept, if I keep a gas here, there is a concept, it is called mean free path. Okay. Mean free path. Gas molecules collide and there is a concept of mean free path. If you see gas cylinders, gas leaking out of gas cylinders, they do not go uniformly. Okay. If you could see, okay, by a microscope how the molecules are moving, they will have some zigzag motion because there are collisions between the molecules. There are collision between the gas molecules. This is an important thing. What is mean free path? Mean free path is average. Again, the word average is very important. Average distance that a gas molecule traverses between two successive collisions. This is a very important concept because you know what we have been doing is very idealized. We have to come closer to real world and you can find out that, which I will do in details in the next lecture, that it is roughly proportional to n pi, okay, d square with some constant here which I cannot find out. Okay. You can check whether I am writing this expression correct, density of particles, and this is the diameter of the molecules. So, I am assuming molecules have a finite size. Okay. Assuming molecules having a finite size, this is the diameter of the molecule, this is the density of molecules. Now, if you assume the limit, this I will prove in the next class, I am just telling you a bit about it. If we assume the limit n goes to 0 or d is 0, okay, they are very small in compared to the other length scales of the problem. This quantity is very large and the approximation I was making that there is no collision, okay, between it hits two walls, okay, and I neglected all the collisions. That is not true if n is very large and d is appreciably large. If they are very small, this fellow goes very high and I can make this approximation. So, here I stop telling you that there is a role of finite size, okay, and you see I always talked about low density, so that mean free path is very large. Okay. There is a size of the gas molecules that has to be taken in consideration, that brings in the concept of mean free path. That is useful in many cases. Even if you consider free electrons in a metal and you consider the conductivity, you use some free electron theory, and that free electron theory also needs a concept of mean free path. I will stop it here today. Thank you.